Jim Miller, thank you so much for having me to VCU, Virginia Commonwealth University.
Yes, in our sort of new nuclear engineering program here.
Yeah. Well, I want to hear about that, but I want to hear about your life story as well. I know that you are an industry veteran who's come back to teach. Yes. Praise your soul. So tell me, how did you get started in this space to begin with?
Well, actually, I'm a child of the 50s, so to speak, so I'm really old. And interestingly, I wanted to be an astronomer.
Astronomer?
And when I was in high school, at that time, I wanted to be a paleontologist. And my mother, who was obviously much wiser than I am, she said, "What do you want to be?" Paleontologist. And she didn't know what that was, but it didn't sound very like a good career, digging up things. She said, "Why don't you be an engineer?" Well, that sounds really boring, So I went to college, majored in physics, came out, went to graduate school in astrophysics. Vietnam War was going on, went to the Navy for 4 years, not the nuclear Navy.
Okay.
Came back into graduate school.
What did you do in the Navy, by the way?
I was a communications technician, Naval Security Group. I guess I'm not supposed to talk about that much.
Some point things have to become declassified, right?
Yeah. And quite fortuitously, I got mononucleosis, so I was back in graduate school the second time, and I was noticing that there were postdocs there in astronomy that were still looking for a research position or something. And one of my friends was a nuclear engineering student, graduate student, and one day he was visiting me, and I was laying in bed there, thinking like, is this a good idea? And he this is sort of elaborated. He leaned over to me and he said, "Jim, come over to the dark side." And so I transferred to nuclear engineering and got a master's degree. And then my first and only job really was at Dominion Energy.
So you get your master's degree. What do they teach you back then? What did they teach you in the master's program?
Pretty much the same you get today. And that's one of the things I think we'll talk about a little bit as to nuclear engineering education. What can we do to improve it? Are we really teaching the right stuff? Yeah. But it was a very good education. I was at Penn State. And because of what I did in the nuclear industry, actually, overall, my courses are probably more relevant than, for the most part, that a typical nuclear engineer would do. They might be a system engineer or something like that. But in the 30-some years at Dominion, I essentially did, might term it R&D or methods development. So we looked at we had to document and come up with ways to do calculations.
Well, let's start at the beginning. What was your first job when you first got into Dominion as a fresh master's nuclear engineer?
Interestingly, it was sort of the same situation when I came here because they were just starting up an in-house nuclear engineering group.
So Dominion, what did it look like at the time? How many plants?
We had the 2 reactors at Surrey were actually operational.
Where's Surrey?
Surrey is down on the James River across from Williamsburg.
Okay.
And their heat sink is the James River.
Okay.
And they were building 2 at North Anna. So they have a heat sink there. The Dominion got the property rights to all the land up there. They dammed up the North Anna River and created Lake Anna. Dominion owns the coastline there, the shoreline of the lake. But they allow all the homeowners who build on the lake to access to the lake and everything, being good neighbors and stuff. I actually got to tour the North Anna units under construction.
Oh, cool.
Which was really neat, although I didn't understand much of what I was seeing at the time. My education background was mostly in reactor physics. And I think it was so I took a couple mechanical engineering courses like heat transfer or something, but it was the next to last semester at Penn State when my advisors said to me, "Jim, do you ever wonder about what happens outside of the core in a nuclear power plant?" And it's a good question because I said, I have no idea. So took a course in power plants, and got some experience there. But I started at Dominion working in reactor physics, and we were just developing the models and everything then.
And what's the models? The models, because the fuel type is going to be pretty standard, right? It's just your typical rods and assemblies. The assemblies go in about the same amount in these big reactors.
So when we say models,
something.
we mean the computer codes, the computer programs.
And what year was this?
It's 1975.
So 1975, what did computer codes do?
Well, whatever they did it very slowly. So we had something code to actually calculate the distribution of power in the core and the criticality conditions. Okay. And the one we were using was pretty much the standard is called PDQ. That stood for pretty damn quick. I'm not kidding you. It was proprietary, so you could not take it out of the country or
Dominion
anything.
owns.
Yeah. No, we actually, it was, I think, developed, it was probably a national lab, I'm guessing. IBM then developed their own version.
IBM got in the nuclear code game?
Yes.
Get out of here.
Yep. And we bought their version of PDQ, but we had access to the actual source code, which means we went in there and made a lot of changes and everything over the years. But the one thing Dominion did that was very smart back then, the same thing Duke did. At that time, most of the nuclear utilities were dependent on the vendors like Westinghouse or GE, whatever, to actually do all the designs and defend any design changes with the Nuclear Regulatory Commission had been created by then. And Dominion and Duke both said, it probably would be in the long run better if we had this in-house expertise, because one thing, they would have our interests at heart. They could look for changes and stuff, we wouldn't have to go out and pay a vendor or something for that. So I'm not sure that would happen today, because it seems like industries today, businesses, everything is expediency. If something doesn't show an instant return. And this is something that was not going to show any return at all for a few years. It was about 3 years before we were into the point that we could do the first core design. We did that.
Why did it take so long to build up that expertise in-house?
You have to, so these computer codes are not like off-the-shelf things, so it's not like you get Excel or something and you say, I'll just set up a spreadsheet. You actually have to build the plant design into them, the fuel design and everything. You have to specify that. You have to get all the input data in there. You have to massage that. You have to benchmark them. Okay, so you need data to show they're actually giving good answers. And this is outside of the actual whole regulatory thing, because you don't want to, do safety analysis calculations. I know we're a little sensitive about the word safety there, but, one of the areas I actually worked in the 3 principal analysis areas of the company over the years. I started in core design, went to safety analysis, went to fuel performance, and fuel design.
What makes core design different than fuel performance and design?
Okay, so these are typically the 3 main areas. So the fuel design actually looks at the performance of the fuel rods and everything. We're looking at material performance, corrosion, make sure you don't overpower them, make sure you don't, exceed the burn-up limit imposed by the Nuclear Regulatory Commission. In other words, how much energy you can get out of them.
Why is there a limit on burnup? Shouldn't the limit be on structural integrity of the cladding? Is that a dumb question?
No, that's a very intelligent question. And the only answer I have is that's the way the game is played from the Nuclear Regulatory Commission.
Okay.
I'm sure we'll have a few more words to say about that. Core design is how you actually arrange the fuel assemblies inside the reactor core. And you have 2 goals there. One is you don't want to violate any of the safety limits, like burn up. Okay. And the other one is you want to optimize the energy you get out, so the economics of the thing. Now, interesting story here. You don't learn all this in school, of course. So I was there a few months, and they sent me to this course at RPI taught by a industry engineer who had lots of years of experience. He might have been an academic. So we had a lot of new young engineers in there who were all going to work in core design. except one was starting out the Nuclear Regulatory Commission. And the instructor is explaining the limitations of these programs. So every computer model, computer code, of course, it has constraints over which you can use it. There's uncertainties on the predictions and everything. And he was saying that because of the nature of the physics and the assumptions made in these models, that if you get out to the periphery, the outside, the boundary of the reactor core, you're going to be off maybe a few percent from what the actual values are of the power there. Now, no one cares. Even the NRC doesn't care because all the action is taking place where the higher powers are. The highest powers are never on the periphery because neutrons leak out there and everything.
Right. Okay.
Well, the one student who was working for the Nuclear Regulatory Commission had no experience in this or anything, right? Just like everybody else in the room except for the instructor. He gets very upset.
Just at the 1% difference.
And he says, 5%? I find that unacceptable. So the instructor is trying to explain to him, this is reality, And the other people in the room, like myself, are thinking, this could be a problem. If he's going to be regulating the future regulator.
Yeah.
And I think some of our concerns there we came face to face with in the following years, that some of the demands by the licensing authority were just, you have to, as you point out, you have to step back and saying, does this really matter?
Right.
Is this what we should really be focusing on?
Right. I was recently at a presentation in Slovenia, and one of the instructors there, Leon, he gave a whole presentation on understanding the difference between know how and know why. Right. And if you understand the know why, the 5%, you can say, that doesn't make much of a difference. But if all you know is know how, and the rules say 5%, 1% maximum, then that's the rules. And you get kind of trapped in a little path there.
That relates to thing that happened, experience I had in the first nuclear engineering course I took, Reactor Theory 1, right? And it's a very challenging subject matter. You're talking about neutrons and solving these complicated differential equations and stuff. And probably about 2 or 3 weeks into the course, one of the students is really getting frustrated, and he says, I don't understand why we're learning all this when we have the computer codes that give us the answer. And the professors, at the time, I didn't quite appreciate his answer, but the professor said, how do you know the codes are giving you the right answer? So you have to have experience in everything. You have to recognize when garbage in and you're getting garbage out, or you're using you're applying the code to an area that it's not benchmarked for, or you can't trust the results, So you have to have experienced engineers in there too.
Yeah, it reminds me of like when you're a kid in math class, like early on, and they're like, well, we have a calculator. Why would I learn calculus if I can just plug it in the calculator? Yeah, that's right. And the calculator's not going to screw up, but even so, you want to develop an intuition for some of these things. So it's important to understand theory.
Definitely. And along those lines, originally, when I started out in the industry, I think if not many, or if not the majority of the NRC regulators actually had experience in the nuclear industry. Over the years, I think it has shifted away from that. So you get new people coming around out of college that are going to regulate the industry, and they haven't seen the other side. Yeah. And that might be one reason that a lot of these things just don't make sense to them.
Yeah. It's a challenge. So I want to touch upon that a little bit more and about what you teach your students and how you convey this. But before we move past it, I mean, you spent a long time at Dominion. What are some of the highlights there? What are some of the really big challenges that you solved throughout your career?
Mainly it was introducing new codes, new methods, So Dominion did not stand still, and every time you had a design change that we want to look at, and some of these changes, for instance, we had to upgrade the plants.
Mm.
So you're now getting more power than you were before. So it's almost like adding, another partial plant to your grid and everything. So life extension. So the plants were originally licensed for 40 years, which is, if you actually look back at it, these plants were designed, the Generation 2 plants now, they were designed back in the 60s and maybe 70s, early 70s at the latest, right? Yeah. Using slide rules. They had computer codes and everything, and the old hand-drawn blueprints. And I spent many an hour looking at these things, to set up models and stuff. They have performed incredibly well because at the time, no one, there was really no evidence they were going to even last 40 years. And now we're going into up to 80-year life extensions. So we had to support all that. There was always crises. Then now another good reason to have this in-house expertise and not having to depend on an outside contractor or a vendor or something is you would have unexpected things, or the station would come back and say, can we do this? And so we are the experts on what the actual licensing requirements are, what the realities of,
So give me a couple examples of these crises. Let's use this opportunity right now to teach people what's the real world like. Like what actually happens at a power plant that demands immediate attention, that we need to put on our thinking caps, that we need to address these quote unquote crises.
So the accidents, we quite like to refer to them as events or unanticipated events, but the accidents, the ones that you design for, they're in 4 different classes or conditions. The ones are normal operating things. Okay. The ones with the possibly greatest consequences, but also the least frequency, are called the condition 4. These are the big ones, So the biggest of the big ones is a large brake loss of coolant accident, which of course never happened.
Crazy that all of our theory is based off of something that's never happened.
One of these is called the steam generator tube rupture.
Yeah.
So
that's when you're breaking the boundary between the primary and secondary coolant.
Very good. Yep. And it's actually a small brake loco or small brake loss of coolant accident, if you think about it. They actually had one of these at North Anna. And the difference between pre-TMI and post-TMI was we had all these trainings now. We had simulators at all the stations. So normally a reactor operator's job is very boring. You refuel, start to plant up to full power, take a bunch of data. Routinely you take data, check instruments and everything, check the systems. Mostly you're just standing there for 18 months.
Yeah.
And then you shut down, refuel again.
Yeah.
Right. But a good idea with the training, besides more knowledge, more understanding of the stations, is it actually breaks up that monotony. They go there and,
I mean, listen, I've had reactor operators even kind of call in or write me emails and being like, listen, I'm so bored. Like, you've seen the industry. Can you give me some idea of other career opportunities? Because literally I'm just sitting here doing nothing.
A nice thing about Dominion is when I was there, and actually my daughter now works for Dominion in the department I retired from.
Well, and what did was she a nuclear engineer as well?
She got her bachelor's degree in mechanical from here.
Congrats. That's
Went to NC State and got her master's in nuclear. Wasn't my idea.
That's awesome.
It was
must be proud though.
Yes, definitely. And now she's at the group I retired from.
That's amazing.
Where was I going with that? Oh, yes. So she tells me it's still true that Dominion is very encouraging of transfers.
Yeah. Otherwise, people are just going to lose their minds from the boredom.
Yeah. And not only transfers within the nuclear business unit, but transfers maybe in the finance or some other part of the fossil side or something like that. Yeah. I was really content with the analysis. I transferred once, spent a year in operations. And I had probably the same reaction. This is really boring. Get me back to math. Get me back to the analysis.
Let me do some deep thinking. Yeah.
And other people would be you sit there and you look at a computer screen for 8 hours and you work on coding and you run these tests and look at data. They might think that's just awful, but I just loved it.
Yeah.
So
that's awesome.
You just have to. But again, reactor operators now, if they actually want to go, up in their career path, probably the most challenging position, maybe in the whole company, is the shift technical advisor then.
Hmm.
This was put in after 3 Mile Island. So one of the problems in 3 Mile Island was ignorance.
Yeah.
It was a sort of a routine malfunction.
Yeah.
The reason they had the meltdown was because the operators did not understand what was going on. They made the wrong decisions, lack of training, bad ergonomics in the control room. One of the key instrumentations was like behind a cabinet or something that they...
So let me ask a question. What would have happened if the operators hadn't touched anything? What would have been the result? Would the plant have safely shut down? And
they would still have had a small brake loss of coolant accident.
Yeah.
But it would have probably been okay because, again, the plant design was fine.
Yeah.
So when the system knew they were losing coolant, so the safety injection came on to replace that coolant.
Yeah.
They didn't think they were losing coolant, and they were concerned about overpressurizing the system, right? So they turned, and they also said, hey, if we have a real problem, maybe we shouldn't be running these safety injection pumps, and we might need them, if we have a real problem. So they turned them off.
So why was the lesson learned from TMI that we need more human input, more humans in the room, more training? Why wasn't the lesson to just get rid of the humans and just always have a fail safe, and if it shuts down, and this is how it's going to go?
Probably, I would say the same reason you don't have technicians doing the design as opposed to engineers, because how do you know the computer code is giving you the right answer? How do you know the instrumentation isn't broken? And that's what happened at TMI. There was a malfunction. The safety, the designs of the safety systems, they cannot possibly consider every possible scenario.
But is it possible to imagine a safety system that's designed in a way that it just always defaults to an economic loss, but in a way that, prevents, hazard? Like I brought this up, I was with the NRC a couple weeks ago, and I was like, why don't they just do it so if there's any dig a hole, dig a 300-foot hole in the ground, and if there's ever like a problem that just, can't be solved and pressures get too high and temperatures get too high, you just drop the core into the hole and bury it, and that's the end of that. And that way you don't need humans around. That's less of a safety hazard because there are less people involved. And then over time, our algorithms and we set things up better and better. So it's just a matter of economics, detailing design, rather than this idea that, we have humans and then there's a risk factor and then there's more systems and systems on top of systems and defense in depth and more systems. Why not just drop in a hole?
I would love to have more people like you at the NRC.
That's what Host said after I brought that up too.
I really don't have an answer to your question as to how foolproof or fail-safe all that would be. Just run. I think it's very feasible. Especially with the new designs, so you're looking at, reliability and everything, more economics, built into that. It's going to be cheaper. Of course, new designs, talking about passive safety, generation 4 designs, low pressures and everything. Yeah. We have the molten salt reactor, where if the core overheats or you lose off-site power, you simply drain the core into underground tanks.
Yeah.
Solve the problem that way. Completely passive, so. Yeah,
it would be amazing to see a lot of these technologies come to fruition, but there's the burden of proof on the reactor designers is so high. It's $1 billion burden of proof even for a light water reactor that we know how it works. Imagine what the burden of proof is for a new set of chemicals, alloys, materials that we've never worked with, new types of pumps that we've never worked with. What's the burden of proof going to be to bring it to the market in the eyes of the regulator?
Well, when the nuclear industry started, of course, one reason there was so much overkill on the regulatory part,
they were
essentially following Admiral Rickover's lead. So when he, designed, looked at building nuclear navy, had no experience with this technology and everything, you said you're going to err and on the side of conservatism or on over-conservatism. The same thing for nuclear industry. Now, that probably made sense back then.
That made sense in the eyes of a a defense contractor, a submarine, a military operation. That's
although
if you're underwater, like.
And they had some accidents, some of the prototypes, EBR-1 and so forth.
Yeah.
But the Nuclear Regulatory Commission, in my opinion, it still think it's the 1970s. They haven't made any, allowance for what we learned in half a century.
Yeah, and we've learned so much about radiation and the true hazard as well. I keep coming back to the fact that, like, Chernobyl taught us so much, but it's like we took all the wrong lessons. What Chernobyl taught us is that the only way someone can get hurt from even the worst type of accident, you got positive reactivity, the thing blew up, the thing caught on fire, spread radiation, as much radiation as you could ever imagine, far out. And then the only isotope that actually hurt people was iodine-131. All protection systems should just be iodine-131 protection systems, and not this like whole thing of like try to contain everything, try to bundle everything up. It's just like if you have a population that isn't malnourished from the perspective of iodine, no one could possibly get hurt.
Well, you have some other ones out there too, but
what we've learned, I think 20 years later,
yeah,
20 years later, now we know the cesium didn't hurt anyone, the strontium didn't hurt anyone. Chernobyl taught us the only dangerous isotope in terms of moving around the environment and getting into humans is iodine-131.
Well, we learned a valuable lesson from 3 Mile Island. So something good came out of it. It was a fact that the analysis codes, look at these type of accidents, the core meltdown and everything, were way, way over conservative.
Yeah.
That it didn't have all those massive releases that you would have.
Why were they so conservative? Something still strikes me as a little odd. I'm trying to track this down, so maybe you can help me with this. Why was it so over conservative? When I read that, like WASH 740 or WASH 9 or WASH 1100, whatever these reports were, they're literally talking about like tens of thousands of deaths. But that's just so far from reality that it's like was something corrupt there? What was going on?
I cannot give you a definitive answer.
But something is wrong there. Like it's not just conservative when you're telling people that a nuclear accident will kill so many people. We know that's not true. Especially for a light water reactor.
A couple theories.
Yeah. Okay. Throw them out.
And one is, again, we're going back to Hiram Rickover.
Yeah.
And, that we built reactors based on the naval designs and everything. So that was probably one thing. The other thing is, this might sound a little conspirational, but if you look back then, there were full-page ads when the nuclear industry was getting started in papers and stuff, warning about the dangers and the hazards of nuclear technology. American Petroleum Institute.
Really?
And
they're afraid. They're threatened.
Yeah. So it was competition.
That's why I'm afraid that's why I think we got to bring them in the loop on this moving forward. Otherwise, they'll just crush us. They'll crush. They got so much money, so much political influence. Like unless we bring in the fossil industry on nuclear technology, they'll just destroy us.
And certainly from a safety aspect or a risk aspect, it's definitely not a level playing field.
Yeah.
As you pointed out in your talk there, you're looking at the lowest risk type of producing power in the world.
Possible.
Yeah.
No one's even explained to me how a light water reactor meltdown could even kill someone. Like literally, I've asked like hundreds and hundreds of engineers. I'm like, paint the picture, show me. Like, tell me what happens, what moves, where the radionuclides go, how do they persist in a concentration that someone would actually get hurt? Like nobody's really been able to demonstrate that a light water reactor is a hazardous device, even in the worst case scenarios.
I agree. It's all embedded in the culture, as you said. Yeah.
And sometimes I talk about like an apartment building is more dangerous because you got like a ton of people in an apartment building. Any one of them have candles, could light a fire, could burn down the whole building. And yet we don't have, fire inspectors permanently stationed at every apartment building. And that's somewhere where hundreds of people could die. A light water reactor, no one can die.
My property has an easement for a natural gas pipeline. One of the major ones in the area.
Yeah.
Right? It has a valve house on the back corner there.
Of your property?
Of my property. And then the house next door, they just built a pig launcher there. You know what a pig launcher is?
Oh, yeah. It's the thing that goes in the tube to inspect it from the inside out.
Yeah. Well, usually when people ask me that, I say, well, it's like a trebuchet. You put this pig in this. Yeah, that's.
Oh, you didn't expect it now, huh?
It's a robotic. Yes, I didn't.
My previous world's robotics.
Okay. Yeah, that's what it is. So apparently the federal government is starting to take another look at gas pipeline safety. So they had to go in there, and the pipeline's never been maintained or anything. So one thing they did is put the pig launcher in. It does not inspect the line that's on my property, though, which is a more local line. And then they had to go in and replace the valve house and replace some of my line there. So to do that, they had to build a bypass line with a couple of valves on it. I'm out there watching them dig up my property and everything.
Sorry.
And I noticed that one of the bypass valves is directly under a power line.
Could it create a short, or what's the?
Well, if the thing's leaking and you have a power line, probably a small probability. Anyway, I called the foreman over and I said, is this all right?
Yeah.
And he looks and he gets this horrified look on his face. Oh, God. No, they never looked up. And there was never anybody inspecting them. So they had to take another couple weeks, move the valve before they actually activated the bypass.
Thank God you saw that.
Well, I mean, again, probably nothing would have happened, but it's, you can't imagine anything happening in the nuclear industry like that.
I know. I know. This is why I think that the nuclear industry is just so concerned with people's public perception. And it's just not true, because we see natural gas stuff blow up all the time. It's like every week there's another explosion. It's not like people rally up and say, I don't want these. I mean, even you didn't say, take them to court and sue them and say, I can't have this on my property, right? It's like people deal with it. When people see accidents, they understand that's part of life. They deal with it. And people only really get scared when the professionals themselves act scared. And the nuclear industry has been acting scared for the last 50 years.
Well, of course, I mean, a good analogy there is fear of flying.
Right.
You have an airline crash and big news and stuff.
Yeah.
And yet people will go out and do all sorts of crazy stuff every day, like drive.
Yeah.
Or they're texting or something like that.
I was checking my email on the way over here. I was like, why am I doing this?
Oh, I'm sorry, I actually.
Oh, man. So, yeah. Okay. So, all right. So, where were we? We were walking through your career.
We were going my career, nuclear safety.
Actually, I want to hear how you became a teacher afterwards, because I'll tell you, I don't know how we can both have an education crisis and we can have like an old people not having enough to do crisis. Why don't we make all retirees teachers of some sort? Now, sure, okay, not everyone's equipped for it, but at least the super educated people like you who've had amazing engineering experience. Why isn't every retired engineer from industry now a high school engineering teacher, a college engineering teacher? How is this not the way we've structured society?
Maybe because many of them don't want to teach.
Too bad. They owe it to the next generation.
Well, I always wanted to teach.
Yeah.
And one reason I actually started in astronomy, because I saw myself teaching college, I thought that'd be the greatest thing in the world to actually have a captive audience there.
Yeah.
And, tell them about the wonders of the universe. Right?
Yeah. Well, you're a good storyteller too.
Oh, thank you. So it's just kind of fell in my lap.
Yeah.
So back in 12 years ago now, maybe, they started the nuclear engineering program here. And that was at the bequest of mainly Dominion Energy, because last century, there were two nuclear engineering programs in Virginia, one at University of Virginia, one at Virginia Tech. They both had research reactors on campus. Near the end of the century, because the nuclear industry was stalled and, it's kind of drying up here for a market, both universities discontinued their nuclear engineering programs, and they decommissioned their research reactors.
What a shame.
Virginia Tech has since started one up. The School of Engineering here, or the College of Engineering now, is only about 22 years old. And Dominion is looking around and saying, well, it would really be nice if we had a closer source of prospective employees than having to go out of state all the time and everything. So they approached VCU, and VCU School of Engineering said, that sounds great. It would fit right into our mechanical engineering program. So they started it up. You probably know Sama.
Yeah.
Yep.
Yeah, I was just with her. Where were we? Maybe in Slovenia. Yeah.
Everybody knows Sama.
Yeah.
So one of the proudest moments of my career, I think, was when she actually met somebody who knew me and didn't know her. Very unlikely to happen. So she had co-taught one of the first courses here with a retired UVA professor, and then she went to the International Atomic Energy Agency for 3 years. Yeah. So they had another coworker of mine who had a doctorate degree. He was teaching a program here. He didn't feel qualified to teach reactor theory, though. Mm. So he asked me, started as an adjunct, and I'm not sure it was out of desperation or whatever. I'm now a full-time professor.
That's awesome.
I'm a teaching faculty. Again, I don't have a PhD. All I do is teach courses, but don't do any research or anything. But also, I'm in charge of managing and developing the nuclear reactor simulator that we have on campus as a teaching tool. So after 3 Mile Island, all commercial power plants in the United States, nuclear power plants, have to have a simulator that's pretty much an exact mock-up of the control room to train the reactor operators and so forth. We have a similar thing here, but our goal is a lot different. It's actually as an educational tool. So the chances of getting a research reactor built in downtown Richmond, probably slim to none. Plus you need a, much more costly infrastructure to maintain it and run it and everything. So one of the first professors, Sam might probably had something to do with this, said we should develop a reactor simulator. And so it's in the room down the hall. It's in the radiation lab, actually. And most universities have these, and you can actually go out and get one or run on a USB drive. By developing it in-house, we actually have control over how we do it and everything. So you run it, it's emulating actually the Kewanee plant, which was a Dominion plant that was decommissioned a few years ago. It's a 2-loop pressurized water reactor, which is all you need because other than being a little less power production, everything, all the systems are there and everything. And you can replicate reactor operations, so you can change power and everything. You can look at the behavior of the reactor. You can have accidents.
Okay.
And we have the animation there and everything. Yeah. So if you have a loss, some accident, you're going to lose your secondary side heat sink. You'll see the water levels and the steam generator going down. And we have enunciator panels, which will alert you to different reactor safety trip set points going off, and they light up, and we put sound effects in there. And
let me ask you, since you mentioned it, what are the differences in terms of advantages between a 1-loop, a 2-loop, a 3-loop, a 4-loop PWR? Why are they different amounts of loops?
Well, one thing is the safety culture of redundancy. So the bigger the reactor is, it's also, if you're going to have everything going through 1 loop, you're going to have a lot bigger pump. If that fails.
And then how come they don't bring that down to, or why don't they continue that theory down to 20 loops or something? Have smaller pipes that are more standard, smaller pumps that are more standard. I mean, it's still surface areas at the end of the day, what you want. Right. And your steam generators, you're making 20 identical smaller steam generators, which makes them more manufacturable, more cheap, easier to construct, easier to swap out and repair, rather than like 2 giant ones that nobody knows how to make except a couple companies.
That's a trade-off between cost and engineering effectiveness or safety.
At the end of the day, isn't it roughly the same amount of steel, given that you're just trying to do surface area? Most of the steel is inside, since you're looking for surface area?
No.
Why not?
Basic geometry. So if you're going to build a reactor, you want to have the least surface area to volume, because the smaller the surface area to volume you have, the less chance the neutrons are going to leak out and escape and not be used. Okay, so the ideal shape for any reactor is a sphere. Mm-hmm. Okay. The molten salt reactor, I've actually designed where the molten salt reactor has the fuel dissolved into the coolant. Actually works on this principle. So when the coolant comes into the spherical core, the leakage is reduced so much that it goes critical. When it leaves into the pipes, now you have this big surface area versus volume. So many neutrons leak out, it goes subcritical.
Yes. Okay. So that's for the reactor core. So for the steam generator.
Heat is essentially just like moving neutrons. Actually, we have the more simplified reactor theory is called diffusion theory because it treats neutrons essentially like heat moving through the reactor. Okay, so you have a lot more piping. You're going to, it's actually for to move the same volume through, you're going to have a lot more expense in actual piping and everything. Mm-hmm. Of course, you can make, and you still have the pressure is going to be the same everywhere. Mm-hmm. So if you need a 2-inch thick pipe to maintain that pressure with one loop, you'll still need a 2-inch thick pipe if you have 20 loops.
Got it.
Called Pascal's principle. So,
got it.
Good question, though.
So
this is how my wife thinks. You know, she keeps asking. So why don't you do this?
Yeah, I guess all these questions stem from the fact that I'm so terrified of when equipment gets so big that it exits like the standard supply chain. I'd rather buy something that was made for 20 applications, that there's 50 vendors that can supply it, even if maybe it's not as efficient. I feel like there'd be tons of cost savings just from buying something off the shelf.
Why does everything have to be nuclear quality in certain parts?
Yes, tell me why. Yeah, why?
Again, that goes back to the culture we had back when the nuclear industry was created by the licensing authority.
So, can anything be done to change that?
They are sort of moving that direction. So, the one big area in the department I left of nuclear analysis that was not even a thing as far as standard analysis went when I was an engineer was probabilistic risk assessment, PRA. So you're going into there. They now have a new 10 CFR 50.69, I think, that says that the license holders can go out if they can show from a PRA analysis that certain parts are, systems are not that important to maintain the integrity of the core and prevent radiation release. You might actually be able to not only reduce the amount of maintenance or the frequency of maintenance, you might be able to use cheaper materials.
And how come nobody's used PRA plus the real world experience from Fukushima to say that there is no risk to the public? That yes, there's maybe a risk of radiation release, there may be a risk of meltdown, but there is no risk to the public because you never get enough concentrated radionuclides in the environment in a way that could ever hurt somebody. And thus, we don't need any safety.
I think it's been done.
It's been done.
But how do you convince the license people?
How do you?
That? I don't know. It's...
Yeah.
People like you and I are looking at this and saying, this is insane. You know, we're probably talking more of a political and sociological problem here than we're talking about technical. It's just like the whole so-called nuclear waste issue. It's not a technical problem.
Right.
It's political.
Right.
It's perception.
Right.
I don't see anything wrong with you take the high-level waste, vitrify it.
Yeah.
Okay. And by waste, I mean the fission products that have no economic value. Not any of the fuel, of course. Take a high-level waste, vitrify it.
Vitrify means put in glass.
Yeah, put in a glass-like structure because then it doesn't have any, chance to get in the groundwater, to move and everything. Just dump it in the deep ocean.
Right.
It's putting out some heat. And actually, apparently, heat sources in the deep ocean will attract more life and everything. The radiation levels are
minuscule. Well, when you dilute anything, radiation becomes totally ineffectual.
Sure.
Yeah.
As a matter of fact, there's evidence that if you would live in a radiation-free environment, you would actually be a health hazard.
I know. But this goes against the whole linear no threshold theory, which is so stubbornly persistent.
Yep.
What do we do about that?
I know what I like to do with it.
Yeah.
And I like to do with the whole licensing process. There's a slow evolution here that in some things...
But we don't have time. We got climate change to fight. Nuclear is the key tool to do it. We don't have time for a slow process. We can't wait 20 years for the nuclear industry to reform these things. It's got to be done in a couple years, and there's no reason it can't be.
So, once in a while you get a little crack in the armor here, that then normally something else happens to patch it up and you're back where you started. So I think back around 2000, Congress, then trying to shake some of this loose from the licensing, they actually told the NRC that, we just don't think you need to do all these constant inspections of the plant. Yeah. And they actually were able to turn the responsibility of plant inspections over to the plant management.
Yeah. So what happened?
Nothing. Everything was fine.
Yeah.
Didn't have any, increase in instances or anything. Right. Of course.
They still have resident inspectors on site now, right?
Yeah, I think they do. I'm pretty sure they do.
Yeah.
So on the other hand, this is, I think in the 1990s, we had this document called the Final Safety Analysis Report.
The FSAR.
FSAR. Yep, FSAR. All the plants have to have them. That's your whole, what they call the design basis is in there and everything. So for some reason in the 1990s, the NRC got the idea that we need to turn this into a living document. So every time you make a design change, you have to keep it updated, okay? Not that you don't have documentation of all that changes and it's all been verified and checked and stuff. So just another level of expense.
Yeah.
Not only that, they said, before you start keeping this thing dynamic, updating it, you need to go in and identify all the facts in there.
What does that mean?
Yeah, good question. What's a fact, Oh, we leave that up to you, but then we will review it and, let you know if indeed you've identified all the facts, right? And that way, what's important in there. Well, everything is probably important in there. You're not going to have this. It's the safety analysis basis for the. So we had these people going in, and we had to come up with some sort of own definitions here as to different types of facts. So some things are obviously facts, but everybody knew them. Gravity. You don't have to have documentation that gravity is going to make things fall and stuff. And then there's other things, of course, that were very nuclear specific or something. And it was definitely something you had to be aware of. So we divided this thing is 16, 17 volumes. Each one's a big notebook full, thousands of pages, right? So we divided this up among all these engineers into different systems and everything. So because I was cognizant of the safety analysis and the core design, I was on those teams. They were called Design Licensing Basis Review Teams, and the acronym for that was the Dilbert teams. Wasn't that appropriate?
Yeah.
So instead of doing what my more important job was to, do the R&D for new methods of analysis and, get verified new computer codes or models or write new codes and models to do things. I spent many a weeks on these teams going over line by line of this document and having, is this important? Okay. Is this correct? We did find some errors.
Yeah.
Okay. Nothing really critical, as I recall, but obviously in something that size, there's going to be some errors. But was that really worth it?
Yeah.
I doubt it.
Probably distracted people from the more important things.
Yeah, well.
I know. This is why sometimes I feel like safety for safety's sake can make things less safe. There
was actually a contention after a lot of the retrofits that were required after the 3 Mile Island.
Yeah.
That I know some engineers felt that they were putting so many additional safety systems in there. It was actually reducing the.
That's right, because complexity is antithetical to safety.
Yeah, the more you can have that will fail.
That's right. Or that you lose track of over time, or that because, there's just so many things that creep in when you have extra things in there that you don't need. Like even in terms of like human behavior, it's like. It's just more for people to, mix up or forget about or even lie about in some cases.
Oh, speaking of that, I don't think I ever finished the story about the steam generator tube rupture accident.
Oh, yeah. Tell me.
Yeah,
tell me.
So we actually had one at North Anna.
Yeah.
And talking to some of the operators on shift when it happened, they said, of course, all the alarms go off and everything. And it breaks out in a cold sweat. What's going on? But because of the simulator training, they're looking at all the signals and everything, and we've seen all this before.
Yeah.
We've seen it several times. It looks like a steam-generated tube rupture.
Yeah.
And it pretty much took care of itself. I mean, there are certain actions they, made sure were going on. And
what
everything.
happens when it takes care of itself? What does it just trip the reactor, drop the control?
Well, first thing you do is you trip the reactor.
Yep.
And then, mainly the system, if you don't want to overpressurize, so there's relief valves that are open to take care of that. You will, after you trip the system, you cut off the fission reaction.
Yep.
But you still have to get rid of that decay heat. So all the fission fragments are mostly radioactive. All radioactive decay puts out heat. For a big unit, at the time of trip, about 7% of the power is decay heat.
At the very moment that it trips.
At the moment it trips.
And then it exponentially decreases from there, right?
Yes, and it actually goes down pretty rapidly because those short-lived radionuclides will decay out relatively fast. So within a day, you're probably under 1%, but then it just goes slow. And 1% of like 3,200 megawatts is still a lot of heat.
Yeah. So then it's funny, once again, because it's like all of these requirements that make a nuclear power plant expensive have made it so we have to go bigger and bigger in order to make it economical. But in theory, you could imagine if you just went smaller and smaller, had a bunch of mini reactors, like all in the same room next to each other or something, that at some point you're so small that even if something happened, the decay heat would be so small that it wouldn't melt through the structural material and you'd just be fine. Everything would stay within the vessel.
Well, bigger is not necessarily better.
But we've kind of been forced down that road.
Well, and that was, I think, definitely a mistake. So as part of the economics nuclear power plants course I teach here, half of the course is engineering economics.
Yeah.
And you realize that it all has to do with time value of money, interest rates and everything. So indeed, if everything goes off the plan, you might show that economy of scale works. Okay. But of course, it never went to plan.
Never.
Before the industry turned around from this atomic energy ruling on environmental impact. I'm not sure if you're familiar with that.
No.
That was really the turnaround. It was, I think, 74 or something. So right before they created the Nuclear Regulatory Commission, indeed, it's just not the NRC, the AEC, same mentality and everything. There was an Australian economist who's done a study, and he said, before that, the cost and time to build a nuclear reactors are just going down. Like any new technology, you have the startup additional costs, and then it will go down and finally level off. He said that was a turnaround point. So the AEC came up with an issue of the new water quality environmental impact standards or something like that. I can't remember the details. And so until they were able to give them time to figure out how that's going to impact the nuclear industry and all the regulations, they put all construction on 18 months hold.
Oh, no. Oh, no. Because if you're borrowing capital for that period of time without being able to generate revenue, your interest payments are just going to go through the roof.
And he said, by his calculations...
What year was this?
Should have it here. It's 1971.
Oh,
DC
no.
Circuit Course case. Calvert Cliffs required the AEC to comply with a mandate to prepare environmental impact statements for proposed actions. The AEC reacted by suspending all licensing for nuclear power plants for 18 months while it devised new rules.
Oh,
so
that was the death of the nuclear industry.
That was it. And according
right there.
Now, according to this economist, and of course, who knows how accurate this is, he said if things had stayed on course before that mandate, if that nuclear power would be 1/10 of its current cost today, and that was a figure you mentioned.
That's right. 1/10. It's the only energy source on planet Earth. Everyone gets abundant energy, clean air. We would have saved 150 million air pollution deaths over the last 50 years. I mean, we'd be living in a utopian society.
And that's still with the Generation 2 plants.
And that's still with the Generation 2 plants. That's crazy. I'm so glad that you brought that to my attention. I didn't know about that 18-month hold. That's unbelievable.
You can keep that.
I mean, this one decision I will attribute towards unconscionable human suffering over the last 50 years.
Several people have done that. Yep. So just on the same vein here,
Yeah.
I told you about the Dilbert teams. Okay, this is an example of how things go astray. A couple of recent things in the field to show you that things have not improved. So I'm probably on the other side of this. Yes. Generation 3 plants, the AP1000. So one of the goals in those designs were, we're going to meet all the NRC's requirements, what they've been complaining about all these years. We'll have passive safety. We'll have simpler systems, still have redundancy and everything. Did all that. Okay. So it's an evolutionary design. Nothing really new here. It's just things that are simpler and better, right? Mm-hmm. In 2018, the NRC approved the issuance of a combined operating license for 2 AP1000 units at Turkey Point. The review took $35 million because, unlike many regulatory agencies, the customer must pay the NRC for the reviews, right? So how long did it take to do this review of something that's pretty much similar to everything else that's going on before, if not better, right? 9 years. How can any industry survive such a thing?
Let me ask a question, because I think this speaks, and we got to wrap up, but I want to hear your thoughts on this. Every other industry, like, okay, if GM was pushed with that issue and the Department of Transportation is like, listen, we need a whole seatbelt review, too many people, this, that, whatever. And GM had to fill out licenses. GM would hire an army of lobbyists, the best marketing people in the world, the best lawyers in the world, and they would not let it go on for 9 years. It would be a 6-month affair tops, and they would spend $100 million making sure, that it was that short, because you'd be losing billions of dollars. Very easy economic calculus for an industry to make, not be stuck for 9 years, versus $100 million worth of lawyers and marketing people. How come Westinghouse allowed for a 9-year review process to happen?
The industry has, the Nuclear Enterprise Institute, the INPO and everything.
They do the opposite. They advocate for more safety systems,
yes.
Longer licensing. They're literally doing the opposite of their job.
I don't have an answer. It boggles the mind, doesn't it?
Yeah. Okay, well, we're about running out of time. We always end on an optimistic note, so I want you to paint the picture for the future of nuclear energy and what you think can happen to paint a brighter world.
I'm really excited about the Gen 4s. And, of course, that begs the question as to, with the integral fast reactor experience at Idaho, right, they had this liquid metal fast breeder reactor, EBR-2, that ran for 25 years without an issue. You looked at the Gen 4 liquid metal fast breeder reactor design for sodium cooled, it's the EBR-2 scaled up. Okay, 25 years since that plant was shut down. In 25 years, certainly we could now be having large liquid metal fast breeder reactors running, low pressure, more inherently safe, if that's really where you're going at this, You're using up the all this, uranium tails out there from the enrichment. You're just burning that and breeding plutonium and everything. Why? Why not?
Jim Miller, thank you so much for your time, your insight, and thank you for teaching. I think that is truly awesome.
I enjoy it. So thanks for having me.